this is one of the things that makes social choice interesting. And there are also some computational complexity results. So some of those were good, like hardness results for manipulation. Those would be good news. But some of them were bad news, such as hardness for otherwise nice voting rules, such as Kemany's rule. Like Kemany's rules in particular is a very attractive rule because of maximum likelihood estimation, yet it's NP hard to compute. Right? So that's bad. So what can we do about that? Well, so this is a room of computer scientists, so I expect an answer like, okay, we can try approximation algorithms, we can try fixed parameter predictability. Well, social choice has its own answer to these sort of questions, and it addresses not just algorithmic aspects, but also like existential aspects, kind of impossibility results. And this is considering preferences that have additional structure. So this is what we're going to discuss now. Preferences are really completely arbitrary. So if you look at real-life preference data, it's very far from being a uniform distribution over all possible orderings of candidates. Right? So they have structure, and if voters' preferences are structured, impossibility results may disappear, and algorithmic complexity results will disappear. And we'll see some examples of both. Right? And we start by defining these structured preferences for which this is the case. Right? And then we'll talk about nice properties that they have. Right? So the specific domains I'll be talking about are single-peaked preferences, single-crossing preferences, and also some somewhat more esoteric preference domains. Okay, so let me start with single-crossing preferences. Okay, how many people here are familiar with this concept already? Just so I have a lay of the land. Okay, so half, but not all. So hopefully, even for you, there will be something interesting eventually. Okay, so we say that preferences are single-peaked if they have this feature. So we can order candidates on the line, left to right, A to F, so that the following holds. For each voter V, there is his top candidate somewhere on this axis, and now if we have two candidates that both lie to the right of the top, D and E, then V prefers the one that is closer to his top to the one that is further away, so D to E. And also, if two candidates are both to the left of the top, our voter prefers the one who is closer to her top to the one who is further away. Okay, so why is this single-peaked? Well, let's see it graphically. So let's consider this voter. And let me use this bar to denote the intensity of preferences. So C is the most preferred candidate, then B, then D, E, F, A is least preferred. Right, so this is single-peaked with peak C. You can see that our condition is satisfied. So B is preferred to A, D is preferred to E, E is preferred to F. Right, and you see, if you look at it as a geometric shape, there's a single peak that this shape has. Right, okay, here's another example, kind of just going from left to right would also be single-peaked with peak A. Or this E as a peak, then move slightly to the right, then all the way to the left. Right, so this is single-peaked. Okay, so when do we encounter single-peaked preferences? Well, remember the example that we started with, the UK voting example, with Conservatives, Labour, and Liberal Democrats. So I talked about it being an example of kind of left-right political parties, and indeed it maps really nicely on the line. Right, so I added the UKIP, the right-wing UK party, just kind of to show you the bigger part of the spectrum. But if you look at voters' preferences, all preferences shown here with respect to this axis, you can see they're single-peaked. So we can go Conservatives, Libs Dem, Labour, Labour, Lib Dem, Conservatives, or we can start with Liberal Democrats and then go either left first then right or vice versa. So UKIP is not included. What wouldn't be single-peaked here is to say first Labour, then Conservatives, then Liberal Democrats. Right? That would not be single-peaked with respect to this axis. Right? And indeed, this is the sort of preference you don't see very often. Okay, so another example where you typically have single-peaked preferences is water temperature at the beach. Right? So some of us prefer slightly warmer water, some of us prefer slightly colder, right? But it would be unusual for someone who like 20 most, then 23, then 25, and then 27 again more than 25 or 23. Right? So if you have a preference, so your preference can decline kind of slightly with some intensity to the right, with some intensity to the left. I'm not going to predict how, but but in a setting like that, you normally have one peak. Okay. Room temperature, by the way, is more complicated, right? I'm talking specifically about water temperature because with room temperature, you may legitimately have two peaks. Why? For being in a t-shirt and for being in a jacket, right? Right? But yeah, but then I still think probably not more than two. Okay, so here are some nice features of single-peak preferences. Well, remember we had this phenomenon of a Condorcet cycle. Majority prefers A to B, majority prefers B to C, Yet majority doesn't prefer A to C. Majority prefers C to A. So there's a cycle, right? Or you don't have a transitive closure, right? So transitive closure would tell you that if you have A better than B, B better than C, you should have A better than C, but instead you have that, right? So that was the counterintuitive behavior of majority preferences. So in fact, we have the whole chaos theorem. So with single peak preferences, there is no chaos. With single peak preferences, weak majority relation is transitive. Okay, so why I'm talking about the weak majority relation. What is a weak majority relation? Right, I say that A is weakly preferred to B if at least half of the voters prefer A to B. So it can be exactly half. Right, in general, I cannot hope to make this theorem that majority relation is transitive with single peak relation with single peak preferences. Because, for instance, the preferences can be, okay, so what can they be? So one voter goes, so this is my axis, A, B, C. One voter goes A, B, C. The other voter goes C, B, A. Right, so if you look at the majority preference relation, it consists of ties. Right, so there's nothing particularly interesting about the majority preference relation here. But weak majority relation is kind of A is weakly preferred to B, B is weakly preferred to C, A is weakly preferred to C. So the claim here is that if I draw the graph for weak majority preferences, then I will have transitive closure. Okay, so why is that the case? So why does it hold? So we'll prove it in two steps. So first we'll prove a lemma, and the lemma will prove that the lemma says that in single peaked elections, there is always a weak Condorcet winner. Okay, so what is a weak Condorcet winner? This is a candidate preferred to every other candidate by weak majority of voters. Again, this example tells you that you're not guaranteed a proper Condorcet winner, but here, in fact, everyone is a weak Condorcet winner. So now, if you don't have single peak preference, you're not even guaranteed a weak Condorcet winner. Again, majority cycle, majority prefers A to B, B to C, C to A, right? No weak Condorcet winners. Right? So this is really a feature of single peak preferences, that you're guaranteed to have a weak Condorcet winner. Right? And now, once we have this lemma, the rest follows by induction. So more precisely, so suppose we have the lemma. We'll prove the lemma in the next slide, but suppose we have the lemma. Then we can do the following. By the lemma, there's a Condorcet winner, weak Condorcet winner. Let's call him A. So he's preferred to everyone else by majority. So in the majority preference ranking, he will obviously be ranked first. Okay, so put him on top. So now delete A from all votes. Look at this majority preferred candidate, delete him from all votes. Now a feature of single peaked preferences is that if you have preferences that are single peaked with respect to an axis, and you just erase some point from that axis and look at the remaining preferences, they're still single peaked, right? So you have this single peaked structure, you just sort of erase one point from it. Obviously, you don't grow a second peak by doing so, right? So it remains single peaked. Okay, so this means once you have deleted A from all votes, you still have a single peak profile. So now by inductive assumption, you have another guy who is a weak Condorcet winner, so you can put him second, right? So, and again, this is legitimate because he's weakly preferred to everyone else by majority. And in this way, inductively, you construct a majority preference order, right? And when you do this, right? So you know that so A, whom you've put first, is weakly preferred to everyone else by majority. Next guy weakly loses to A, is weakly preferred to everyone else. So you have constructed a ranking, and this ranking is indeed the weak majority, consistent with the weak majority relation. Okay, make sense? Questions? Yes. So it may be ties. Okay, so it may be ties, so it may be other things, right? So I'm not saying that it's all ties. I'm saying that I allow for ties. Both, right? So that the feature, okay, that the feature of weak majority, kind of weak majority graph. It may have edges going both ways, right? Okay. Transitive in the sense that if I have just in the sense of a graph. So if I have a edge from A to B and B to C, right, I'm guaranteed an edge from A to C. There may still be an edge from C to A as well, right? I'm not ruling that out, but I'm saying that if A, B, and B, C are there, then AC must be there. So there may be more, but AC must be there. Right. Yeah. So there may be ties. And in fact, okay, so if you're not happy with these ties, so let's just assume them away by saying that we have an odd number of voters. So if we have an odd number of voters, there are no ties. And this argument, right, so if you apply this argument and in the context of an odd number of voters, it gives you actual Condorcet at every step. So if you have an odd number of voters and single peak preferences, then exactly kind of by this argument, you get a transitive majority relation, kind of proper majority relation, and proper Condorcet. Okay, so now let's prove this lemma, right? So I'll prove it for kind of weak Condorcet and possibly even number of voters. But as we go through it, we can also keep in mind the odd number of voters and see that in that case we actually get a strong Condorcet, like proper Condorcet. Okay, so that's the lemma. So how do we prove the lemma? Well, okay, let's order the voters according to the top choice. So this is my axis with candidates. So let me associate each voter. So voters are these little green boxes. Let me associate each voter with his top candidate. Right, so this is how voters are placed. So in some positions there are no voters, in some positions there are several voters. Now let me find the median voter. Okay, so suppose first I have an odd number of voters. Right, so like in this picture. So if I have an odd number of voters, 2k plus 1, let me look at the voter k plus 1 as I go left to right. Right, so here I have 3 guys here, so I'm looking for the fourth voter, so fourth voter would be here. So there can be several of them in this place. In that case, I'll have a hard time deciding which one of them is fourth voter, but they all have the same top choice, so it doesn't matter to me. So I can choose arbitrarily. So I'm looking for the median candidate k plus 1 as I order them left to right. Okay, so now let me look at the top choice of that candidate. So let me look at this red dot next to which I have the median green box. I claim that this is a Condorcet. Well, why? Well, if you think about any other candidate, right? So let's compare. Okay, so here I have my purple guy. So so I want to compare him to some other candidate, say this guy, and I'm asking how many people prefer purple guy to this guy. Well, so voters' preference are single peaked. So everyone whose peak is to the right of purple guy, so their preferences are declining that way. So all these green guys over there prefer purple guy to this red guy, right? And this of course includes the guy whose preferences are right there, right? So purple guy is his top choice. And because he's the median guy, so there's at least half of the voters are to the right of that point, right? So at least half of the voters prefer purple guy to any of these guys. Okay, and same in the opposite direction, of course, symmetrically. So if you take the candidate, here and ask how many voters prefer purple guy to this guy, so it will be this green guy and everyone to the left of him. Kind of all of them kind of have their preferences kind of shaped this way. So they prefer purple guy to that green guy. So again, we have a majority. So for whatever pairwise preference whatever pairwise selection you look at, you have a majority in favor of purple guy. So in fact, a strict majority, right? Because you have the central guy and half of the remaining guys, so that's more than half. Okay, so if you have an even number of voters, it's slightly more annoying. So I tweaked it slightly to make it an even number of voters, right? So now I claim that we can have a whole bunch of weak Condorcet. So weak Condorcet are everyone between top of the k's voter and top of the k plus first voter, right? If you have k plus 1 voter. So everyone here is a weak Condorcet. Why? Well, by the same argument. Okay, so let's take this purple guy here, compare him to anyone to the right. Well, all the voters kind of here and to the left prefer this purple guy to anyone over there, right? So that's half of the voters, right? And all voters, right, if we compare purple guy to this guy, again, we have, in fact, this time more than half of the voters preferring him to this guy, right? So in some cases, it can be exactly half, right? So he's a weak Condorcet. So for instance, if you compare, okay, so what should we compare? So we should ask how many people prefer this purple guy to that purple guy, this to that. Well, these four voters prefer this one to that one. Those 4 voters go the other way around, right? So it may be a tie, right? But in each case, we have at least half of the voters preferring each of them. Okay, questions? Okay, good. So, like I said, okay, so the lemma shows that we have a weak Condorcet winner for odd number of voters and for even number of voters. And in the previous slide, okay, from that lemma, we concluded that the majority preference order, weak majority preference order is transitive. Okay, so that's good. So at least we don't have majority cycles. So here's another nice property of single peak preferences. We can circumvent the Gibbard-Satterthwaite theorem. Right? So Gibbard-Satterthwaite did this very powerful result that every voting rule is manipulable. Now, when preference is single peak, I'm going to give you a voting rule that is not manipulable. Right? And again, it's based on a very similar picture and very similar concepts. Suppose now that we have an odd number of voters. You've seen that an even number of voters causes kind of complications that are not fundamental but just annoying. So let me focus on an odd number of voters. So suppose we have an odd number of voters. So median voter rule proceeds as follows. It considers an election that is single peaked with respect to an axis. So here's an axis. So it asks each voter to vote for a single candidate. So in that sense, it's like plurality, but it doesn't then operate like plurality. So each voter votes for one candidate. We map the voters. So we map the voters here on the line in the same way as in the previous slide. We associate each voter with his top candidate. And again, we choose the median voter. So we order voters by their top choice, breaking ties arbitrarily, and look at the median voter, voter k plus 1, and we output his top choice. Right? So it's even simpler than what we did in the previous slide. We look for the median voter and output his top choice. I claim that this voting rule is not manipulable. Right? So that truthfully reporting is your best choice. So in fact, it's a dominant strategy in game theoretic terms. It's the best you can do no matter what everyone else does. Okay, so let's try to prove that. Okay, so this is our median guy. So why is median truthful? Well, okay, so let's consider a voter in our order. Well, if our voter is this lucky guy, k plus first guy, he gets his most preferred candidate. Of course, he doesn't want to manipulate. Now, suppose not. So suppose, okay, without loss of generality, so let's consider a candidate that sits to the left of the median, right? So one of these guys. Right, so he can jump around. He can vote for another candidate, which means moving his rectangle to another point. Well, what can he accomplish by doing this? Well, he can move somewhere so as to remain to the left of the yellow point. For instance, he can move a little bit to the right, or in the same fashion, he could move a little bit to the left. And if that happens, this doesn't change who the median voter is. Right, so the median voter is still that guy, no matter how this one guy jumps within this part of the picture. Right? And then, so the median guy doesn't change, the choice of the median guy doesn't change, right? So this is not a manipulation because it doesn't change anything. Okay, he can be more ambitious and jump all the way to the right of this guy. Okay, so here he is. What happens now? Okay, now, well, he accomplished something. He's now the median voter. And generally, even if he doesn't become the median voter, maybe the identity of the median voter may change, right? So it may become, so for instance, if he jumped even further over there, assuming there was something there to jump to, then the median voter would be one of these guys, right? So he can change the identity of the median voter. Is it a good change? Well, no. So now, because now, in this case, the median voter now is him. So his declared top choice is this point, and this is further to the right. And his preference is single peak. So if his top choice was there, then he prefers the yellow guy to this guy, right? His preference is declining like that. So this is not a good manipulation for him. So he can accomplish something, but this something is not good for him, right? And therefore, he doesn't have a beneficial manipulation. Okay, makes sense? Okay, so yeah, so single peak preferences are wonderful. So let's try to understand them a little bit better. So I gave you one definition. So this is the definition I gave you. Yeah. So this median voter rule, right? So the voting rule looks how everyone votes, finds the median voter, and outputs his top choice. So this is a voting rule that is not even defined if you don't have the single peaked axis, right? So this is a rule that operates depending on the axis. Yeah. Yes. Right. So the yes, and this is what we used to argue that the manipulation was not useful. Right? So that was the point. So to say that this manipulation moving to the right was not successful, this was the point where we crucially used that preference to a single peaked. Right. So to implement that rule, you need n axis. To prove that it's truthful, you need preference to actually be single peaked. Yes? Well, so in a way, I'm just asking them to vote for one alternative. Right? So I don't really care what they report. Right? So because I'm only yeah, okay. So I agree that it's a fairly subtle point. So so in a way, so if he now reports something, okay, so I assume that the axis is given to me as part of the voting rule description, right? And if I have that, I just ask them to vote for their top choice, right? And if they report something that is not even consistent with the axis, I just ignore that altogether and look at his top choice only. This is all I need to run that rule, right? So the rest of his preferences are only needed for the correctness proof, not for the implementation of the rule, right? So that's actually another nice feature of this rule, that it takes very little communication. Yeah, I do need to know the axis, right? And plausibly for a single peak profile, there may be more than one axis. We'll actually talk about that later. And with different axes, it might seem like you may have different choices. And we'll talk about that later. Right. So again, very good question. So if the axis exists, if the pref's a single peak, but we don't know the axis with respect to which it's single peak, how can we figure it out? Okay, so, and we'll spend quite some time on that later in the tutorial. But yeah, thanks for kind of raising the issue. Okay, further questions? Okay, so some equivalent definitions. So they will be useful in some of the things we do. Right, so I gave the definition that is most intuitive to me because it explains what it means to have a single peak. There are a couple more definitions that are actually very useful for the proofs. Right, and I think they're also intuitive once you get used to them. So alternative definition 1 says that the preference is single peaked if it has no values. So in what sense no values? Well, imagine this axis, kind of ABC. So ABC is now my axis. ABC, okay, let me add D for fun. ABC. Okay, a value would be something that goes like that. So preference ranking, in which I have three things kind of on the axis, A, B, C. So when I write less, kind of this kind of less sign, I always refer to the axis. Right, so a value is three things kind of ordered on the axis as A, B, C, such that B is the least preferred candidate out of A, B, and C. Right, so this picture. Right, so if this is the intensity of preferences, right, so that would be a value. Right, and if preferences are single, so the definition is we say that preferences are single peaked if there are no values. Right, so that's an alternative definition. We are going to prove that it's equivalent. Right, and in a way, okay, so if you have just one peak, you cannot have values. Right. So I think intuitively this should be clear, but we'll also prove it formally. So here's another alternative definition. So this another alternative definition is very useful for generalizing the notion of single peakedness, and we'll see a few examples of that. So what this definition says is the following. So a vote is single peaked with respect to an axis if we look at prefixes of that vote. Top candidate, top 2 candidates, top 3 candidates, top 4 candidates. Each of them forms a contiguous segment with respect to an axis. So again, let's see an example. So suppose you have a vote going like that. So B, then C, then A, then D. So that would be B, C, A, D. Right, and you can see that kind of top choice is contiguous, then top 2, then top 3, and finally top 4. Okay, so again, sort of makes sense. So now let's prove formally that all these 4 definitions are equivalent. So maybe you can help me with the proofs a little bit. Okay, so first, suppose we have preferences decreasing from the peak, like this is our basic definition. So let's prove that from that it follows that there are no values. Okay, so suppose for the sake of contradiction that V ranks B last of ABC. Okay, suppose now that top of V, the most preferred alternative of B, is to the left of B. So it can be A, it can be something else, but it's to the left of B. Okay, So why is this? Okay, so the top is, well, there somewhere, right? Okay, why is it a contradiction? Right, because if the, exactly, so because if the top is there somewhere, then as we move from the top towards B and C, the preference are declining, so B is closer to the top than C is, so B should be preferred to C. So a contradiction with the assumption that B is ranked last of ABC. Right, and another possibility is, so symmetrically, so if top is, okay, if top is to the right of B, then we have this picture, and then of course, kind of, since top is to the right, then B should be preferred to A, right, because preferences decline like that, right, and again, this means that B is not the last. Okay, so that was an easy one. So if preferences are decreasing from the peak, there are no valleys. Okay, so as you ski down the mountain and you ski smoothly, right, there are no valleys. Okay, so, okay, third definition talked about contiguous segments. So suppose we have no valleys, we'll argue that there are no contiguous segments. So we are going to prove the equivalence of all three definitions in a sort of cyclic manner. Right, so we'll prove no valleys implies contiguous segments, and then we'll prove that contiguous segments implies our standard definition. Okay, so suppose for contradiction, so suppose we have the no valleys property, and we suppose for contradiction that the set of top k candidates is not contiguous for some k. So let's pick the smallest such k. So A, B, C, D is this kind of prefix of the vote, right? So this is my vote, and it's not contiguous on the axis. So there is some guy C, there's some guy Z who breaks it up when we look at the axis. So in the vote, A, B, C, D is a contiguous prefix, but if you look at it on the axis, it's not contiguous there. There's something sitting in between, right? And this thing that sits in between, let's call it Z, right? And it appears somewhere further down in the vote. Okay, so now your job is to find a valley. So give me a valley, someone. Right, so remember what a valley is. So three things on the axis going left to right, so that the middle one is ranked below the other two. So anything involving Z, like BZD or AZD, any of those, right? So Z in the vote appears below all the red things, right? So that would be a valley. Okay, so that's that. Okay. Okay, so finally, suppose we have contiguous segments. Let's prove that kind of preferences decrease from the peak. Okay, so suppose for contradiction that preferences do not decrease from the peak. So the voter's top choice, top V, is top V. Then we have D and C on the axis, but our vote actually prefers C to D. So the preferences are not single peaked according to our standard definition. Okay, so how can, so, okay, so this is the axis. So let's say A is the top choice, right? So we have contiguous segments on that axis. Okay, so top, then D, then C, yet V prefers C to D. Okay, so then, okay, so now you can see that contiguous segments, contiguous prefixes properties failed, right? Okay, so how do we prove it? Okay, so what is the contiguous segment here that is broken? ABC, right? So formally, kind of to make it kind of slightly more general, so suppose, okay, so suppose voter B ranks C in position K, so then it ranks, okay, so it ranks D in position K plus 1 or lower, so because he prefers C to D, right? And therefore, if you look at the set of top K candidates, right, it's not contiguous because it's broken by D, right? So this is the general argument. Okay, so we now have our three equivalent definitions. So this will be convenient for what we are going to do. Okay, so now let's establish some nice properties of single-peaked preferences. Okay, so first claim is this. Suppose I have a single-peaked profile. So this is basically a quick way of seeing whether a profile is likely to be single-peaked. So the claim is if a profile is single-peaked, then the set of candidates who are ranked last by at least one voter, whoever appear at the bottom of a ranking, has size at most 2. So there can be at most 2 distinct candidates ever ranked last. Okay, why? Yeah, so left and right end of the axis. Right? If a point is not an endpoint of the axis, it cannot possibly be ranked last. Right? So what is the easiest, out of all our definitions, so what is the easiest way to see it? Well, maybe, so maybe contiguous segments, right? So if some point kind of on the, if some point on the, in the middle of the axis, if some guy here is last, right, then the prefix of the first k minus 1 is not contiguous, it's broken by that guy. Okay. Okay, so here's another claim. So if I have a profile over m candidates, so it may be, okay, so maybe it's not single peaked at all. Maybe it's single peaked with respect to some axis, so that, but there can be more than one axis. But there's still a bound on the number of axes. So it's at most 2 to the power m minus 1, and this bound is in fact tight. Okay, so why is it at most 2 to the power m minus 1? So let's reason about it in this way. So let me take a single vote. So let me not bother with the profile. Let me take a single vote. So my vote is A, B, C, D, E, F. I'm trying to construct an axis with respect to which this vote is single peaked. Okay, so I know that this guy ranks F last, so F has to be one of my endpoints, F. Okay, good. I'm crossing F out of here. Now I have to place E somewhere on the axis. If I look at the remaining vote, E is an endpoint, so it has to be either the leftmost point or rightmost point. So I have two options. Option 1 is to put E here. Option 2 is to put E there. And both are legitimate, right? So I have these two choices for E, right? So I'm thinking like of having 6 positions where I'm going to place these guys, A, B, C, D, E, F, right? And once I placed F, I have 2 positions for E. So both are legitimate, right? So now suppose I fixed E, right? Suppose, say I placed E here. Right, so then I still have this contiguous segment of 4 more points, and next I need to place D. And for D, again, I have 2 options, here or here. Right, so for each of the guys, except for the first one, so for the first one I chose arbitrarily that he's going to go here, right, and for each of the remaining guys I have 2 options. Right. So that gives me, okay, so that gives me my 2 to the power m minus 1. Okay, so what bothers me slightly that the first choice was, okay, not quite like that. So for the first guy, I had 2 options. F could go left or right. After that, E could go kind of left or right in the remaining segment. So I'm sort of zooming in on this contiguous segment. For the last guy, I actually have no choice. Okay. Right. Right. Okay, yeah, so same argument. So you can build it from the top, kind of growing it from inside, or you can grow it from outside. But yes, so arguably, yes, so what you said could be easy as well. Okay, so that's 2 to the power m minus 1. Okay, so why is this bound tight? Well, actually, this argument shows that this bound is tight. It can really be 2 to the power m minus 1 if your profile consists of a single vote. Okay, so that's just a warning that in general there can be a lot of axes. Right? If your profile is just one vote, you have all these different axes. Right? So I could have constructed, I can construct, okay, let me do one, for example. So I can do F, E, D, C, B, A, and I can also do, for instance, A, B, C, D, E, F. So there can be more than one axis. Okay, so in which cases do I have a single axis? Well, here is one condition. Suppose I have a single peaked profile, and so I know that it's single peaked, and it contains 2 votes, and these 2 votes are reverses of each other. One goes A to Z, the other one goes Z to A. Then there's only one axis, and this axis is A to Z. Okay, why? Well, here's one way to think about it. Right, so we know what are the endpoints of the axis. Right, these are the 2 points that appear last, and these are A and Z. Correct? Okay, so now you know that A is an endpoint, say leftmost point, and you have this vote going from A to Z, right? So it starts at an endpoint, so it has no other way to go but right, right? So on the axis, kind of the candidates have to appear in order of that vote, right? Okay, so if you want to figure out, whether your profile is single-peaked or not, and you have these two opposing votes, right? Then you're in luck. Then you know what the axis could be. You already have a guess, right? And then you just have to check whether this guess works or not, right? So that gives you a very easy way of recognizing whether a profile is single-peaked. Okay. Okay, so now we understand a few things about single-peaked preferences. Let me talk about a similar but different preference domain. Right, so this is the domain of single crossing preferences. So single-peaked preferences, we were ordering candidates left to right. Well, we can also order voters left to right, and that's not quite the same thing. Okay, before we look at the formal definition, let's just look at the picture. So these are my voters. I have 7 voters here. Voters ranking is again a vertical bar. The first guy goes A first, then B, then C, then D. So I want you to choose so note that I have 4 colors here: red, blue, green, and black. So I want you to choose 2 colors out of those 4, kind of whatever 2 colors you prefer, and sort of try to trace those 2 colors in the picture. Trace their, say, red ribbon and blue ribbon, right? So the red ribbon moves like that, and the blue ribbon moves like that. And what you can see is that the red ribbon and blue ribbon intersect once, right? So here, right, so the intersection point happens here, right? Up to this point, red is above blue. From that point on, blue is above red. And if you picked any other 2 colors for this profile, you would still have that property. Okay, so formally, we say that a profile is single crossing with respect to a given number of voters if for every pair of candidates there is an index I such that up to this point A is above B, and from that point on B is above A. So A and B are allowed to cross at most once. Okay, so single-peaked preferences model kind of political spectrum or things like temperature. Single crossing preferences also model things like that, but in a slightly different fashion. So we say that our voters kind of have a position left to right. So some voters are more left-wing, some voters are more right-wing. So for candidates, kind of it's maybe more difficult to pinpoint them on the axis. You cannot always, but still voters form their preference in some consistent way, right? So voters who prefer A to B are before voters who prefer B to A. Okay, so this is the definition of single crossing. So so this shows you a profile that is single crossing. Okay, let me illustrate some nice property of single crossing preferences. For single peaked, we prove that majority preference order is transitive. Weak majority preference order is transitive. So let me prove the same for single crossing. So again, to avoid headache, let me focus on an odd number of voters. So say I have an odd number of voters, and the proof is, well, effectively a proof by single picture. Let me take the median voter. Right, so this is my median voter. Let me look at his ranking. Okay, so no induction this time. Let's just look at this ranking. I claim that this specific ranking, the ranking that is already there, is actually the majority preference order. That majority agrees with this guy on every pair of candidates. Well, why? Let's pick a pair of candidates. Okay, so pick a pair of candidates for me. A and D. Okay, good. A and D. Well, okay, so this guy says A over D. All the guys to the left of him also say A over D. Okay, so can it be that there is someone on the left who disagrees with him and someone on the right who disagrees with him? No, because then we would have DA, AD, DA, right? So if there are people both on the left and on the right who disagree with him, we violate single crossing condition. So therefore, at least on one side of him, everyone agrees with him on that pair. So that side plus he himself is more than half of the voters, right? And for even number, that would be at least half of the voters. Okay, so majority preference order is transitive. And what is interesting here is that here majority preference order actually appears in the profile itself. For single peak, we constructed it, but there can be examples where the majority preference order is different from the vote of any of the candidates. It's different from any of the ballots we observe. But here majority coincides with one of the ballots that we observe in the profile. Okay, so this also means that the single crossing order of voters is essentially unique. Okay, so we are going to prove that in exercises, but effectively, okay, so I'm not quite going to prove that, but if you can order voters in a single crossing way, so there's basically one order. Okay, so why is it not exactly true? Well, for one thing, you can have several identical voters. You can permute those. The other thing is you can just swap the entire order of voters, right? So take the whole thing and sort of reflect it, right? If the former one was single crossed, then the new one is single crossing as well, right? But apart from that, it's actually unique, and we're going to prove it in the exercise session. But it basically follows by the same argument. Okay, so now we've seen single peak preferences, we've seen single crossing preference. So this is a tentative Venn diagram. So we may ask if this tentative diagram actually matches the truth, right? So is it indeed the case that their preference is single peaked but not single crossing but are not single peaked? So do they intersect? What does the intersection look like? Okay, so let's try first. So let me start by identifying some points kind of here and here to show you that this is a proper Venn diagram. Okay, so this is single peaked but not single crossing. So what I have here is I have 4 points on the axis, 2 outside points and 2 inside points. And my voters are all like this. So first they order 2 inside points in some way, then they order 2 outside points. Now, no matter how you do it, you're going to be single peaked, right? So if you start sort of B, then go to C, or start C, go to B, after that you can order A and D in any way, right? And there are 4 distinct voters that are like that. Right, so the 2 ways of ordering BC, 2 ways of ordering AD, so 4 altogether. I claim that this is not single crossing, no matter how you order these voters. Okay, why? Suppose it were to be single crossing. Let's look at the first 2 voters, voter 1 and voter 2. I claim that they have to be adjacent. Right? This is because of the candidates B and C. Right, so the other 2 voters disagree with them on BC. So if one of these 2 voters comes in between them, then for B and C we'll have double crossing. Right, so these guys have to be next to each other. Right, 1 and 2. By the same argument, 3 and 4 have to be next to each other. Again, because of BC. But now also 1 and 3 have to be next to each other. Right, this is because AD. Right, and 2 and 4 have to be next to each other. Right. And with all these conditions, you just cannot place them on the line so that all these conditions are satisfied. Right? So this is single peak, but not single crossing. Okay, now let me show you an example of something that is single crossing, but not single peak. Right? And it's an interesting construction that gives you some sense of what single crossing profiles may look like. Okay, let me start with a vote that goes 1 to n. Now let me take candidate n and pull him through all the way to the top. Right? As he does that, he crosses all other candidates. So now I have n at the top and everyone else below in the same order as before. Okay. Now next step, let me take n minus 1, pull him past all other candidates except n. I cannot cross him with n because he and n already crossed once. So I pull him all the way up but stop at n. Right? So he crosses everyone and stays there. Right? And I continue doing this. So as I do this, kind of when each candidate goes up, he crosses everyone with a smaller index, but he doesn't cross the bigger guys. Right? So this is single crossing. Okay. Single crossing, so I end with that. Right? So I end with a complete reversal. Okay, who wants to tell me why this is not single peaked? Right, exactly. Yeah, so we argue that in single peaked elections, so at most 2 guys can appear in the bottom positions. Right, so here we have, well, everything you'd like to see in the bottom positions. Okay, so that's clearly not single peaked. Okay, so this is our beautiful Venn diagram. So now let's get to the interesting bit. Let's get to the intersection. Okay, and let me tell you about, okay, so I'm going to tell you about a preference domain that actually sits in that intersection and is so natural that you may sort of wonder why I didn't tell you about it before. Okay, and this is what I call one-dimensional Euclidean preferences. Okay, so when we talked about single peak preferences, we ordered candidates on the line. When we talked about single crossing preferences, we ordered voters on the line. So why not do both? Right, let me just dump them all, voters and candidates, on the line. Right, and let's say, in fact, let me endow this line with the usual Euclidean metric. Or in simple words, let me say that the voter prefers candidate A to candidate B if A is closer to her than B is. Right, so that's my picture. So it's a bunch of voters, bunch of candidates. So for instance, for voter 1, her preference ranking would be B, then A, then C, D, E. Right, so kind of very simple geometric construction. Okay, I claim, okay, so this is my first guy, second guy would be voter 2. So B, C first, then B, A, then D, maybe, then A. Anyway. So my claim is that one-dimensional Euclidean preferences are in fact single-peaked. And they are single-peaked with respect to the order of candidates on the line. Okay, why is that? Well, if you have a voter here, obviously she prefers candidates who are closer to her to the ones that are further away, on each side of her preference order. Right, so this is like the definition of Euclidean distance. Right, so you prefer those that are closer to you. Right, and our definition of single-peakedness just said that it happens on each side with Euclidean preferences. We just have it universally. But okay, so certainly we have single-peakedness. It's also single-crossing. So how do we see that it's single-crossing? Okay, so it's single-crossing with respect to this order of voters. Well, here's how we think about it. So where are the voters who prefer B to C in this picture? Well, let's pick the median point between B and C, our geometric median point. Everyone to the left prefers B to C. Everyone to the right prefers C to B. Right? So this cuts our axis neatly into two halves. In one half we have B over C, in the other half we have C over B. Right? So that's single crossing. Okay. So in the way kind of Euclidean preferences is intuition both behind single peaked and behind single crossing. Okay, now wouldn't it be a nice theorem if one Euclidean was exactly the intersection of single peaked and single crossing? Right, that would be beautiful. Right? Except, yes, our world is not quite as beautiful as that, so this is actually not true. Right, so there exists a preference profile that is single peaked and single crossing, but not one-dimensional Euclidean. So this is the smallest example, I believe, known to humankind. Right, so the first example that was discovered was uglier than that, but this is the simplest. And I will actually be able to prove to you that it has this property. Okay, so we have 6 candidates, 3 voters. It's slightly annoying. It's fairly easy to convince yourself that it's single peaked, right? So the first guy goes B, C, D, E, F, B, C, D, E, then A, then F. Second guy goes D, E, C, B. So basically you can look at, so the easiest way I guess is to look at all prefixes and check that each prefix is contiguous, right? So DE, DEC, DECB, DECBA, etc. Okay. It's even more annoying to check that it's single crossing, right? So you really have to look at all pairs of voters and check that at all pairs of candidates and check that they cross at most ones, but well, they do. Right, so whatever, okay. So random choice, give me some pair of candidates. EC, right? So we have CE, EC, EC, right? So by by PCP theorem, right? So if you give me a few of those choices, you can be convinced. I can convince you I'm not lying, right? Give or take. Okay. So it's single crossing with respect to this order of voters. It's single peak. I claim that it's actually not Euclidean, right? And it's a cute argument that shows that this is not Euclidean, and it will be an illustration of what follows. So let me actually do it. Okay, let me look at voter 1. Voter 1 happens to prefer E to A, right? So if I look at his position with respect to the median point between A and E, so the median point that sits somewhere there, because he prefers E to A, has to be to the right of it, right? So his coordinate X is to the right of this point. On the other hand, if I look at his preference with respect to BC, so he prefers B to C. So he has to be to the left of the median of B and C. Right? So these are inequalities that follow from his preference order. Right? So he's to the right of this median, to the left of that median. Okay. So now let's look at voter 2. So in a similar fashion, so he prefers D to C. So he's to the right of CD, median point. He prefers A to F, so he's to the left of AF, median point. Finally, voter 3. Voter 3 prefers F to B, so he's to the right of this median point, to the left of this median point. Okay, you see the contradiction? We add up the left-hand side, we add up the right-hand side, we get both sums on the same side and strict inequality between them. Okay, so that's impossibility. Okay, so something to note here is that, again, if we look at the definition of one-dimensional Euclidean, right, so we need strict inequalities. So I want all these points to be distinct. Right. So for the embedding to exist, so all these inequalities have to be strict. Okay, so it's not quite equal. So in fact, okay, so there's a characterization of profile that are both single peaked and single crossing. Unfortunately, it's not nearly as pretty as saying that they're one Euclidean, right? It's not nearly kind of as useful either, so I'm not going to go there, right? But now the picture is sort of like that. Okay, so this is kind of, these are sort of one-dimensional notions of structure. So if you don't mind, I suggest kind of splitting, since we have three hours, I don't know, my preference would be to have two 15-minute breaks, unless there's a strong preference for a longer break. But even if you want a longer break, I would rather take it now. Right, so it's sort of a natural place for me to make a break in the lecture. So I suggest that we do it now.